Hello, I welcome you all in this lecture related with the course Failure Analysis and Prevention, and we are talking about the failure analysis of casting. In this presentation, I will be talking about the failure analysis of the cast iron product, namely the Sluice wall. So, in this presentation, basically, I will try to first of all familiarize with the casting. So, basics of the cast iron and then general structure and properties, then typical cast iron failures and their analysis, general strategy to avoid the cast iron failure components. Uh, but whole of the the focus of this presentation will be on the failure analysis of the sluice wall, which is made of the cast iron. Okay. So, as far as the main features of the cast iron are concerned, here cast iron contains the carbon content more than 2%. So, which means the 2 to 4 6.7. So, if the cast iron having the carbon about 4.3% means this is eutectic cast iron. Eutectic cast iron. If it is more than 4.3, then this is termed as hyper-eutectic cast iron. Okay. And if the carbon content in a cast iron is between 2 to 4.3, then it is termed as the hypo-eutectic cast iron. Okay. So, this is the broad classification based on the composition only, means based on the carbon weight percentage. Okay. Now, this carbon when present in the iron greater than 2% can be in variety of forms like free form or combined form. Free form means it is broadly in the form of like graphite. Carbon is present in the form of graphite, while when it is present in the combined form means it is forming some kind of the compounds. These compounds may be in form of say iron carbide, cementite or other alloy carbides. Okay. So, those are like the combined form. Mostly in the plane you can say where the carbon and iron are predominantly present with the controlled concentration or the amount of the other residual elements like the manganese, silicon, etc. So, effect of so these elements have marginal effect on the structure and properties. So, what is that factor which is affecting the type of the form in which carbon is present? It is basically the apart from alloying, the cooling conditions, the cooling rate experienced by the molten metal affects the form in which carbon is present. Okay. So, if the cooling conditions are slow, usually it promotes the graphites. We can say the graphitization, this a common word is graphitization. So, the graphite may be in form of flakes. Okay. When the graphite is in or it can be in form of the nodules. So, the geometrical feature of the graphite dictates the type of cast iron. When the carbon in free form is present in form of flakes, okay, then it is termed as grey cast iron. Okay. When the carbon in free form is present in form of the nodules or spherical balls, it is termed as the nodular cast iron. Okay. When the cast carbon is present in combined form, then mostly it leads to the formation of the white cast iron. Okay. White cast iron. And when the typical heat treatment is done to achieve the typical morphology of the carbon in free form, that is irregular shaped the graphite clusters are obtained in case of the malleable cast iron. So, malleable cast irons are made through the heat treatment. Okay. So, the form in which carbon is present leads to the variety of the formation of different types of the cast iron. Usually because of the high carbon content and the kind of cooling conditions which are observed during the solidification of casting, cast irons offer very high hardness coupled with the very low ductility. High hardness means like say 30, 40 HRC kind of thing. Okay. On the other hand, ductility is very less, maybe like say even less than 1% also. and toughness also like less than 5 joule or even like 2 joules. So, the properties are very, hardness is high, ductility is low, and toughness is also very low, and this makes the cast irons more sensitive to the impact loads. Although these property variations again will depend upon the form in which carbon is present and its morphology or the shape in which it is present, apart from the composition or presence of the other alloying elements. Okay. Say there is one more category in which category or the type of cast iron, that is called alloy irons. Okay. Alloy irons means the elements like chromium is added, forming the chromium carbide due to the presence of high carbon content and leading to the extremely high hardness and very good wear resistance. So, for abrasive wear conditions, the alloy irons are extensively used. So, the carbon content and the chromium content can vary significantly in these systems. High hardness and low ductility, low toughness makes the cast iron extremely sensitive for the stress concentration. Okay, and if there is any defect leading to the load resisting cross sectional area. So, if the cast iron is having defect, then the presence of defects makes them extremely sensitive for the fracture. Okay, and the common issues which are encountered in the cast irons are like porosity, inclusions, and the cracks and embrittlement, that is the low toughness and very low ductility coupled with the high hardness. Okay. So, just for the better understanding, this is the iron carbon diagram. So, if you see here, this is the like the zone or the bandwidth for the cast irons, okay, from 2 to 6.6%. So, this is 4.3% corresponding to the eutectic cast iron, and then hypoeutectic on the left side, and on the right side it is hypereutectic. What it suggests that the cast irons will primarily be having the ferrite or the perlite coupled with the Fe3C as per the iron carbon diagram, but depending upon the cooling conditions, the form in which carbon is present and the kind of compounds being formed can vary significantly. Okay, this is the only purpose of showing the iron carbon diagram. So, these are the common types of cast irons. Here you can say the grey cast iron, ductile or a nodular cast iron, malleable cast iron, white cast iron, and alloy irons. So, if you see, the grey cast iron has the graphite flakes. Okay. So, what you can see here are the graphite flakes. Okay. The matrix can be ferrite, perlite, or even the martensitic one also, depending upon the cooling rate being experienced. Then the nodular cast iron has the graphite nodules. These is spherical balls of the graphite. Then the malleable cast iron is one where the irregular shaped clusters of the graphite are formed through the heat treatment, and white cast iron will have the alloy carbides, means the carbon in combined form, in primarily in form of iron carbides. Okay. So, this has due to the high carbon content and very high cooling rate conditions under which the white cast iron is formed, it will be having the martensite and the iron carbide. Okay, and that Fe3C kind of thing formed, which will be leading to the very high hardness and the very low toughness and ductility. Alloy irons, as I have said, these are alloyed with the various alloying elements, like apart from iron and carbon, there can be chromium, there can be niobium, or other which are will be interacting with the carbon to form their carbides to increase the hardness and the abrasive wear resistance particularly. Okay. Then apart from this, so this was just introduction about the various types of the cast iron. So, this is one particular case study related to the failure of the sluice valve, which was made of the cast iron. Sluice valve is a simple component of the hydropower plant and can be used at multiple other places. This the sluice valve regulates the flow of water during the operation of the hydro turbines, and due to during the operation it is subject to the fluctuating pressure, and also the impact is experienced under the unfavorable operating conditions. And this particular sluice valve, if you see, this is when the sluice valve is in up position, facilitates the uninterrupted flow of the fluid or the water, and when it is closed, when it is in the down position, it stops the flow of the water. Okay. So, when the unfavorable conditions lead to, so when it is stopped suddenly, a lot of internal pressure and the impact will be generated, and that will be leading to the increased failure tendency due to the impact. And this sluice valve was made of, say, the grey cast iron. Okay. So, this is the typical image of the failed the sluice valve, which shows this is like the fracture edge of the sluice valve casing, basically where from it had failed. So, the procedure which is normally used in the failure analysis is like, let us understand the component itself, like background information, wherein you can see what is the item, what was the application for which it was used, what is the design, what are the materials, what are the properties which are expected, and what was the manufacturing approach, etc. This information is collected just to familiarize with the product which is being investigated. So, do the background information collection, and since we have already talked about this, cast iron of a given design and for application is like the making the regulating the flow of water. Okay. So, the next step in after familiarizing this, let us inspect this. So, inspection showed that the fracture surface is having the porosity and inclusions, and the fracture basically triggered from the high stress concentration zone. Okay. Say it is having the casing structure is like this. So, it failed from this area wherever there is a change in the cross section, or the fillet is sharp. So, in those areas where from the fracture was triggered. Obviously, to confirm that the cast iron is made of the component, that is the sluice valve was made of the cast iron of the correct composition or not, composition analysis is needed, so that it can be checked if it is corresponding to the one which was specified or it is different. Similarly, the mechanical property study is needed to see if the component is strong and the hard enough and tough enough to take up the service conditions load. So, mechanical property study is needed, and the microstructural study is also needed to see if it is the really correct kind of the grey cast iron or the matrix of the right kind of the structure or not. And also an stress analysis is needed to understand how far the presence of defect, if they are there in the cast components, they can contribute towards the failure. So, this is done considering the defect size, reduction in the load resisting cross sectional area, and the kind of the stresses that can occur due to the presence of this defect or stress concentration factor. Okay. So, here stress analysis, as far as the stress analysis is concerned, what is important, like say if there is a defect. Okay. The defects can be there in form of notches and of or the casting defects of the different sizes, and the kind of the way by which it is affecting the load resisting cross sectional area, and how the defects are causing the stress concentration. So, stress analysis is needs to be done considering these aspects, like the size of the defect, where it is present, and the how defect is affecting the load resisting cross sectional area, and how it is affecting the stress concentration. That will be determining the maximum stresses that will be occurring in the component. So, the defect in the casting, like say in form of gaseous defects were observed on the fracture surface. So, we try to see like what is the size, what is the shape, where it is occurring, and stress concentration in form of the fillets wherever the change in cross section is taking place, or the geometrical stress concentration due to the typical geometry of the casing, and mechanical properties of the material in terms of the yield strength, ductility, toughness, etc. Okay. So, these are the factors which are kept in mind for the stress analysis. Okay. What it considers is like say if there is a change in cross section or the fillet is too sharp, then the flow lines of the stresses they will be segregating at the location where the change in cross section is taking place. This will be leading to the increased stresses. Increased stresses at these locations will be increasing the fracture tendency, especially if the material is of the low ductility and the low toughness and high hardness. So, if these three are in very deadly combination, if the material is having these three characteristics and the defect is occurring or the stress concentration is occurring in such kind of the materials, then that simply promotes the fracture tendency. And if the fillet or the change in cross section is gradual, then the stress concentration tendency is reduced, and that in turn will be reducing the failure tendency. That's what this is a typical the photograph of a sample which failed from this location where the change in cross section was taking place. The geometry is such that at the bottom the fillet is sharp, and that promotes the fracture. So, this is the importance of the the sharp change in cross section or the stress concentration, how it promotes the defect. Say if there is a defect, say either is surface defect or the internal defect. Internal defect of the size 2A, for internal defect the defect size is say 2A, and for external defect the defect size is A only, that is how it is considered. And the tip radius, like say the radius of the crack tip is rho t. Okay. So, these are the two things, the size of the defect, that is A for open, and the 2A for the internal defects, and the rho t is the crack tip radius. These are the two most important factors. Say due to the externally applied loading for a given cross sectional area, nominal stress is coming sigma naught. Okay. Then for a given nominal stress, if there is a defect of A size for external and 2A size for the internal, then how the maximum stress occurring in vicinity of the defect will be affected. That is what we can see here, twice of sigma naught, that is the nominal stress, square root of the A, that is the size of defect, and the square root out and the rho t. Okay. So, what this suggests that maximum stress that will be occurring will be proportional to the defect size. Greater the defect size, greater will be the maximum stress, that is one, and inversely proportional to the square root of the rho t. Okay, square root of A and square root of the rho t. So, if the crack tip is sharp, then the stress concentration will be too high and your the maximum stresses will be very high. Okay, that is what we can see here also in this diagram. The ratio of the maximum stress and nominal stress is known as the stress concentration factor, and that we can see from this twice of square root of A by rho t. Okay, what it suggests that, like, if this is the internal defect for externally applied stress on the component of sigma nominal stress sigma naught, then how the presence of this internal defect of size 2A will be affecting the stress distribution. So, the stresses will be maximum in vicinity of the defect, and if the maximum stress crosses the ultimate stress limit, in case of the ultimate strength limit, then in case of the low ductility, high hardness and high brittleness materials, the simply crack will propagate, okay, and catastrophic fracture can be observed. But if the material is soft and ductile, then the maximum stress will be causing the blunting of the crack. Earlier it was sharp, now it will get blunted. So, blunting of the crack tip will simply increase the crack tip radius, and the increase in crack tip radius will reduce the stress concentration factor, will reduce the maximum stresses. Okay, that in turn will reduce the maximum stresses. So, this is why it is important which kind of the material it is. But in case of the cast irons, since most of the cast irons are like say the grey cast iron particularly, it is very hard, brittle and very low ductility. Okay. So, because of this combination of the properties, if there is a defect, then it will be causing the high stress concentration, crack tip will remain sharp, and high stress concentration will be triggering the growth of the defects, easily causing the catastrophic fracture without much indication. So, here analysis of observations, like the study was conducted and in this study we try to look for, like, let us confirm if the component design is as per the recommendation, if the material is as per the recommendation, if the mechanical properties are as per the expected ones or not, how about the metallurgical characteristics like microstructure and the composition. So, this is about the confirmation of the things. Whenever the component fails, we need to confirm these things to ensure that if there is any discrepancy or the deviation. We have also to see if the component which has failed had defect or not, and if there are defects, then where they are present, and if their presence can really contribute towards the failure, then for that stress analysis is needed. Okay. And then finally, the conclusions. So, here if we see in this particular case, the fractured components samples were taken and the hardness and tensile strength tests were done. Okay. And the fracture surface, the sample taken from the near fracture surface, middle of the section thickness, and these were measured in terms of Brinell hardness and the Rockwell hardness, and the properties are the measured values are shown here. So, here especially if we see the lower value in some cases near the fracture surface is 209, okay, and while the maximum value is like say 234. So, there is a lot of heterogeneity and variation in the properties, you can say. Okay. And if you see in case of the HRC also, the variation is like say from 55 to 59. So, there is a lot of variation. Similarly, the sample taken from the fractured sluice wall, the tensile tests were conducted, and this shows that the typical the stress strain diagram, and what it showed that the different samples showed the different three samples were tensile test was conducted on three different samples, and all showed very low ductility as expected, and the tensile strength variation was significant, and same was with the yield strength like 91 to 169 and 139 to. So, this suggests that there is a lot of variability in terms of the property variation. So, what can be concluded here, like tensile properties differ appreciably from the recommended grey cast iron for the material of this particular grade. Okay. This is one of the aspects. Uh, Similarly, the toughness tests were also conducted, and toughness test using the sample of 10 by 10 into the 55 mm cube, and this test was conducted at three different temperatures like -30, 0 and 22 degrees centigrade, and the toughness test of the material at the room temperature was marginally higher than that it was observed under the low temperature conditions of 0 and -30, and no major drastic reduction in the properties was observed. Okay. So, this shows that no ductile to brittle transition behavior kind of thing was there, but the values were very low. The minimum value of the 2 joule was observed under the low temperature conditions, but this was expected actually for the cast iron. Okay. Then the composition was cross checked, and the composition of the sluice wall material was found like 0.2 3.2% carbon, 1.7% of the silicon, 0.98 manganese, zero point 0.1 and zero point 0.1 sulfur, and 0.12 phosphorus. These are little higher than the usually accepted ones. The chemical composition of the castings always show marginal variation due to the segregation tendency, because that is the typical feature of the cast irons. When the so this is showing the this slide shows the visual observations of the fractured component. So, this is the entire casting which is failed, a sluice wall which has failed, and where from it failed, that is what shows along this the zone where change in cross section is taking place, and what it showed like the presence of the gaseous defects and inclusions on the fracture surface at all these locations. So, when you have defect especially in the high stress zone, then that becomes one of the main reasons for the weakness of the material. Okay. and it promotes the fracture surface. So, based on these observations, the failure of the sluice valve occurred due to the gaseous defects, because these gaseous defects very large, especially in the highest concentration areas. Stress concentration also contributed at the sharp corners. So, remedy was the increase the fillet radius at the corner, and to reduce the gaseous defects, proper casting procedures including the proper melt treatment, gating design, use of chills, proper ramming of the molding sand, and the permeability of the sand mold is to be ensured. The summary here is the failure analysis of sluice valve was undertaken to investigate the potential causes of failure, and the investigation was undertaken using the systematic procedure of the failure analysis of the components. And what we did, like we conduct the preliminary examination of the failed component, microscopic examination, chemical analysis, mechanical properties, in order to come out with the conclusions like which factor predominantly would have contributed towards the failure. That's all for this presentation. Thank you for your attention.